Hello, we are the MEM 435 Group 7 consisting of Amanda, Craig, Deepu, Philip, and Matthew. Today we will be proposing our final design for a robotic jellyfish for the Center of Aquatic Sciences. The problem statement we are presented with was to develop an educational device that is used for teaching principles of biology and engineering sciences that are taught as a part of the educational programs at the Center of Aquatic Sciences. The product will teach the sensory anatomy of the jellyfish, specifically how most jellyfish will see with the cilia and a lack of a brain. Some jellyfish have specialized structures called ophelia. Inside these structures are different receptors. Our prototype will demonstrate the light sensor, which is called the cilia. The product will teach the concept of feedback control systems, mimicking the thought process of a jellyfish to students. The simple control loop can be demonstrated by the movement of the jellyfish. The input would be the light sensor reading, depending on the feedback from the loop, which compares the input of a light sensor to the desired threshold. The controller is the Arduino, which is used to communicate with the motor when it moves. If the light reading is above the threshold, the motor will move. This is our final product concept, a desktop device of an animal model. Some components will be injection molded, such as the jellyfish parts labeled A, D, E, and F. The frame of the prototype will be built out of clear plastic, such as acrylic sheets. Not pictured is a clear box protected in electronics, while still allowing smooth user operation. It will be assembled by attaching the jellyfish with an electrical cable, which will be wrapped around a pulley system mounted on a frame. The two halves of the jellyfish will be held together using magnets. The function of the cilia and its network of visible, simple, and reactive nerves will be taught by showing how the model reacts to different sources of input, such as movement, sound, and light. This serves as an appropriate model to teach the feedback control systems because of the simplicity of the control loop and the fact that we demonstrate a direct response from the user input. Through our experimentation, the model covers all of the listed crucial functionalities of the final product. The jellyfish will move when light is shown on the photoresistor. The model moves 2 feet in 4.6 seconds, disassembles in 1.5 seconds, survives a 1-foot drop, and the cable holds the weight of the model without breaking. The noted functionalities letters are referenced in later slides. Here is a list of the critical needs and specifications of the final product. Please note that the letters to the left correlate to the crucial functionalities defined in the previous slide. This relates to how our crucial functionalities fulfill our critical needs and specifications. Each need applies to one or more of the crucial functionalities in the prototype.
The purpose of this prototype was to confirm the crucial functionalities of the final product concept with using rapid prototyping technology instead of final production methods. 3D printed components such as the jellyfish model A, the pulley D, the mount E, and the bracket F. The frame B of the prototype will be built out of plywood using screws and glue. It will then be assembled by attaching the jellyfish with an electrical cable, which will be wrapped around a pulley system mounted onto the frame. The jellyfish is split into 2 halves and attached with embedded magnets G. This will allow for the jellyfish to be easily taken apart to show the anatomy. Once the prototype is assembled, experiments with the photoresistor and Arduino can begin to verify the performance. This will help with programming the Arduino so the jellyfish will move only when flashed with intense amounts of light. Now this is a brief overview of our experimental plan, covering 5 different experiments to guide our design choices and prove our critical functionalities. The first experiment is to study the effect of different sources of light on the photoresistor and phototransistor. We evaluated readings from the photoresistor and transistor at 6 different light sources, which include a dark room, a room with low light, a room with all lights on, and a room with all lights on with an iPhone flashlight 3 feet away, 1 foot away, and 2 inches away from the sensor. This experiment concluded that the photoresistor was a much better option than the phototransistor because the readings had more variations. Data obtained helped determine necessary thresholds for the Arduino programming. The second experiment was to verify that the Arduino programming is fully functional and the threshold to activate the movement of the jellyfish is set properly. We evaluated the reaction as a yes or no answer based on movement of the model as a reaction of the sunlight. The thresholds were 650 raw output value for the photoresistor, which is 0 through 1000, and 65, which is also 0 through 1000, for the phototransistor. The resistor was more sensitive, so we decided it would be more valuable as the model. This will not be able to be used outside or directly next to a window, as it would directly react with the direct sunlight and affect the output. The third experiment evaluated the time to take apart the model to display the anatomy inside. The test used 2, 4, and 6 pairs of magnets per time to disassemble the model in seconds. This experiment concluded that 6 pairs of magnets was the optimal amount to hold the model together. Experiment 4 evaluated the strength of the magnets to hold the jellyfish together. The test used 2, 4, and 6 pairs of magnets. The model was then dropped from 6 inches, 12 inches, and 24 inches in differing positions, such as horizontal, front, and side. The result concluded that 6 pairs of magnets are needed to keep the model together because it withstood the most amount of abuse without breaking. The speed of the jellyfish was evaluated with 2 motors and 3 different spool sizes. The spools were 1 inch, 1.5 inch, and 2 inches in diameter. The time to move the jellyfish 2 feet was recorded. It was concluded that the largest diameter spool moved the jellyfish the fastest. From this experiment, motor 2 could not sufficiently move the jellyfish. For our prototype, we decided the 1.5 inch spool with motor 1 would be sufficient. The team based the current design of the prototype on the results from testing. In doing so, we have made the prototype very close to the final product. All but one of the critical functionalities was thoroughly addressed through our testing. The only change we would need to upgrade is the durability of the product. In summary, all of the critical functionalities were met, but there could still be areas for improvement, especially for functionality D, where their model could still be made sturdier. In conclusion, the prototype has proved the final product will meet the needs and specifications and should be developed with the following changes. Thank you for your time and consideration.